that slide and put on the projector. Okay. Now, didn't realize that I failed to announce this in my first class, so I don't know if I announced it in this one. Did I tell you about the college transfer days, Birmingham campus and Bessemer campus next month? Yay or nay? Yes. Okay. And how about the POETS, the Center for Power Optimization of Electrothermal Systems for engineers. It's a summer research program. Did I tell you about it? Yay or nay? No?
He wants to hear about it.
Oh, okay. This is from Mr. Joseph Muskin, could be Professor or Dr. Joseph Muskin, I don't know. Says he runs a summer research program for the Center for Power Optimization of Electrothermal Systems. The acronym is POETS. We are looking to recruit minority engineering students to work at 3 of the 4 institutions this summer. It's University of Illinois, University of Arkansas, and Howard University. This 10-week internship program exposes undergraduate students to academic research in the fields of mechanical, electrical, and material engineering. Okay, so you get to learn an awful lot. I mean, incredible learning experience. What's that? Sure, right after class, okay? Now, not only do you get to learn a lot, they pay you to learn a lot. $5,000 they'll pay you for the 10-week experience. That's $500 a week, okay? That's not bad. When you also consider that you receive free housing, which I think usually includes a meal card, so you get free food for 10 weeks, and they pay you to get you there and home one time. So round-trip airfare one time. You can't come home every weekend, that's on you. Okay? And you gain access to weekly professional development webinars as well as other benefits, and it says see the brochure. You want to be a poet this summer? Research experience for undergraduates in science and engineering. The application deadline is February 15th. So you got a little less than, well, around 3 weeks, I guess.
Did you say Howard University?
Say again?
Did you say Howard University?
Howard is one of the 3, right? And University of Arkansas and University of Illinois. Okay, there's plenty more here. I'll let you read it or take pictures of it. Now, on this, I print on recycled paper, so just take a picture of this side, and if you want to, this side. This one doesn't have much information on it, but this side does. So anyway, I'll let you decide what you want to take pictures of. But anyway, those are things coming up in February. There may be others out there. Check. I know some of you are in Honors College and the STEM program and other things like this. Check with them. There's all kinds of research experience for undergraduates that are available. Take advantage of them. They're really fantastic. Okay. Now. Whoa. Wait, that's the trouble. I want to do with it. Okay. I am pretty sure that we are yuck. Sorry thing. Okay. What just happened here? There it is. Okay. Any questions on anything we've done up till now? Okay. We're in Chapter 11. Just started it last time. Vectors and the geometry of space. 11.1 is vectors in the plane, and we are just starting at the top of page 752, component form of a vector, which is the way to express vectors. Now this, I imagine, is kind of old hat for most of you, so we should be able to go through this fairly quickly. Okay, but let me know if I get to going too quickly, assuming you know something you may not, or have been exposed to, or may have forgotten. Many quantities in geometry and physics, especially physics, but in geometry too, such as area, volume, temperature, mass, and time, can be characterized by a single real number. Area, length times width, or however you want to measure area. Volume, length times width times height, or however you want to measure volume. Temperature, how hot or cold it is. Mass, time, those are single real numbers scaled to the appropriate units of measure, so they're called scalar quantities. They have no direction associated with them. There's a few others in physics. Energy, for instance, is a scalar quantity. Work is a scalar quantity. There are many out there. The real number associated with each of these is called a scalar, or these are scalar quantities called a scalar. Other quantities, however, such as, I like to start with displacement, velocity, acceleration, force, momentum, several things such as that, involve both magnitude and direction, cannot be characterized completely by a single real number. So guess what we call those? Vectors, okay? A directed line segment, okay, is used to represent such a quantity as shown here. Directed line segment. So a line segment means it has an initial point and a terminal point, fixed endpoints. Directed means it's heading in one of the two directions, either in that direction or this direction. It's got to be one or the other. Now, when we name a vector, if the one endpoint is P and the second endpoint is Q, most of the time we let P be the initial point, Q be the terminal point, so you always then refer to that vector as vector PQ. Start with the initial, end with the terminal, and notice the vector symbol you put over that, it points in the direction of the terminal point, Q. Okay? That's a directed line segment. That is what we call a vector. The directed line segment PQ has an initial point and a terminal point, Q. Its length, or its magnitude, is denoted this way. Double bars here, PQ, there's a vector PQ with double bars. A scalar with single bars is called absolute value, right? A vector, or a directed line segment with double bars, is called the magnitude. Now, those two entities have some things in common. They're never negative. Magnitude of a vector is never negative. Absolute value of a number, or a scalar, is never negative. Okay? Trying to think if there's anything else I want to refer to you that way. I don't think so. Directed line segments that have the same length, so this has a length and it has a direction. Okay? They have the same length and the same direction are called equivalent. Okay? Every one of these vectors here has exactly the same length, exactly the same direction. Also one up here or down here, somewhere else. Those would be equivalent directed line segments. Now, so far they haven't used the term vector except in the title, but these are also vectors. One of these slides they'll get around to saying it. The set of all the directed line segments that are equivalent to a given directional directed line segment, PQ, is a vector in the plane. Okay? Now, one of the things I just sort of may have misrepresented by this definition when I was pointing to these things here, I said up here or out here. Well, that's not in the plane. It's in some plane, but the vector v. Now, the way the book denotes a vector is to mark Fred here. All right, so we're only missing Josh. I think I saw him. Didn't I see him with you earlier, Ryan?
No, that was Josh, man. No, not that Josh.
Not this Josh. Okay, I'm sorry. I only saw him from behind, and it was like him from behind. Okay. The book denotes them by bold, usually lowercase letters. That indicates it's a vector. I can't write bold. So how I'll write this is the letter V with an arrow over it, just like this arrow here over PQ. In typeset material, vectors are usually denoted by lowercase, bold-faced letters such as U, V, and W. Those are probably the three most used vector things, but there can be others. Okay. When written by hand, however, this is what I was just saying, vectors are often denoted by letters with arrows above them like U, V, and W there. That's the only way I can do it because you can't tell if I'm writing bold or not bold. Okay, maybe my pen just turned or something. So this is how I usually will refer to a vector. Okay. Be sure that you understand that a vector represents a set of directed line segments. Now this is a little bit bizarre definition in my mind of a vector, because I would call a single directed line segment a vector too. Sure, it may be a set of those, but I won't always draw a bunch of them out there and say that's a vector. In practice, however, it is common not to distinguish between a vector and one of its representatives. We're going to go by the practice. Okay? Each having the same length, same direction. Here's example 1, the bottom half of page 752. Let V be represented by a directed line segment from 0, 0, okay, the origin. This is in a plane, so that's why there's only two coordinates here, to the point 3, 2 in that same plane. Let U be represented, so V is this one, U be represented by the vector directed line segment, 1, 2 to 4, 4. It says show that U and V are equivalent vectors. Okay? Now, what would it take to show that? What is it to be a vector? In parentheses there. Same length, same direction. Now, how do we represent the length of a vector? It's sort of bizarre. They talked about it, but they didn't give you a formula for it. But they sort of expected you to know that. Does anyone know what the length of the magnitude of a vector is? What the formula for it is? The square root of okay, not plus. Well, delta x squared plus delta y squared. If you said it that way, that would be okay. Usually it's done x2 minus x1 squared plus y2 minus y1 squared. That's what I meant by delta. Difference in x's squared plus the difference in y squared. If you're in two space, which we are. So, what would it be for v? And it doesn't really matter which one you name to be 2 and 1. It doesn't really matter. Usually you let the from be the 1 and the 2 be the 2, but it really doesn't matter in this case. Okay, what would that give you? Square root of? Anybody? 3 minus 0 squared plus 2 minus 0 squared, and this would be square root of if you can read my ugly writing there. Second? Okay, the square root of 13. Okay, perfect. All right, so that's the magnitude of V, square root of 13. 9 plus 4, 13, square root of 13. All right. What you want to do next? You want to do U magnitude, or do you want to do V direction? Okay, U magnitude. So let's do that one. Magnitude of U, vector U, would be what? Four minus 1 squared plus 4 minus 2 squared, which would be the square root of 13. Okay, went right to the chase. 3 squared plus 2 squared, same as we had before, square root of 13. All right, they have same magnitudes. Does that mean they're the same vectors? That means they have the same length, but does not conclusively mean they are the same vectors. Because a vector of this length could be here, or here, or here, or here, not the same vectors. Okay? So, what do we need to do to determine what's the other feature to determine? Direction. All right. Now, how are we going to refer to direction? Second? That is certainly one way. So what would be the slope of it? M for V would be y2 minus y1 divided by x2 minus x1, which would be? Okay, very good. This is for V. 2/3. And what would be the slope for vector U? Okay. Say that one more time. 2/3. Okay, I thought you said 3/2. I went, whoop, whoop, whoop. Okay. That would also be 2/3. Hey, same slope, same magnitude, same vector. Equivalent vectors. Okay? Show that these two are equivalent. You've just done it. All right. Are there any questions?
You called it vector and what was the M word?
Say that one more
What was
time.
that M word?
M is slope, yeah. Okay. I'm going to erase what I did, the chicken scratch here, and let's see how they proceed. Let P be 0, 0, and Q be 3, 2, the initial and terminal points of the vector V. Let R be 1, 2, S 1, 4, 4, initial and terminal points of the vector U. Okay? They draw them here. Now, don't trust your vision. Okay? They look similar. They look the same length. They look the same direction. So you might have a real strong suspicion they are equivalent vectors. But to make sure, let's do the thing. You can use the distance formula to show that PQ and RS have the same length. That distance formula, as you all said before, the magnitude of PQ, vector PQ would be 3 minus 0 squared plus 2 minus 0 squared. Because the initial point was 0, 0, the final terminal point is 3, 2. That gives you magnitude of square root of 13. RS, similarly done, would give you magnitude of square root of 13. But this does not guarantee they are the same vectors. What you would have to do there, both line segments have the same direction because they're both directed toward the upper right on lines having the same slope. So here's where the slope comes into play. The slope of PQ is 2 minus 3. That's the change of y over change of x. 2 minus 0 over 3 minus 0 are 2/3. And the slope of RS is 4 minus 2, the change of y, which is 2 over the change of x, which is 4 minus 1, 3, 2/3. Same slopes, same magnitude, equivalent vectors. Any questions? Because PQ and RS have the same length and the same direction, you can conclude that the two vectors are equivalent. That is, U, V, and U are equivalent vectors. Okay. Now, this is top of page 753. The directed line segment whose initial point is the origin, like P was here, is often the most convenient representative of the set of equivalent directed line segments, such as they shown here. So if you take this one, initial point of the origin, that's your standard form for the vector. This is another formulation for it. You translate this without changing direction or length and get it back to standard. So they are equivalent vectors, but this is the one we call in standard form. Okay? That representation of V is to be in standard position. I said form, standard position. A directed line segment whose initial point is the origin can be uniquely represented by the coordinates of its terminal point Q, which is V1, V2. All right. Now, this wouldn't be for any old vector, like the one that was up here. You can't take its coordinates there and say that represents the vector. There you have to do the difference. But if your initial point is the origin, 0, 0, no. From where I'm standing, it looks like that's a bold 0, and that's not a bold 0, but I don't know. Maybe I'm just like, well, that could be an O, I don't know. They don't look the same to me, but that may be my parallax view or something. Okay. When you have a set of ordered pairs in parentheses, that represents a point, coordinates of a point. Now, if this is in standard position with the initial point at 0, 0, that same ordered pair, but put in angle brackets, that makes the components of a vector. Coordinates of a point in parentheses, components of a vector in angle brackets. Now, I know that Dawson right now is in linear algebra. And I don't know if the two of you are planning to take linear algebra. You are, in the summer probably or sometime. Okay, you planning to take it at all, or do you know?
Maybe if I transfer.
What's that?
Maybe after I transfer.
Oh yeah, right. Okay. The book that Dawson and I are using for linear algebra is written by Ron Larson, same author as here. Okay? In the linear algebra book, he represents vectors in parentheses just like he does points. Why the change, I don't know. Okay? But he does that consistently. Now, it was in the older edition. I've just started using the new edition because I just got it. I haven't looked to see if he change that there. So in this text, parentheses mean point, vertical, angle brackets. That's why I call them mean vector. Okay? These are coordinates of a point, components of a vector. They're the same two numbers, exactly. It's just the symbology indicates this is the point, that's the vector. Angle brackets as opposed to parentheses. Okay. In the definition, note that the difference in the notation between the component form of the vector v, v1, v2, and the point, whoa, that should be a parenthesis. And in your text, it is parentheses. Here on the slide guy got it mixed up. Okay? He probably didn't understand math. This is parentheses there. Okay?
Angle brackets mean what exactly?
Vector. Components of a vector. Parentheses means coordinates of a point. So here's the definition of component form of a vector in the plane. If V is a vector in the plane, whose initial point is the origin, whose terminal point is parentheses v1, v2, then the component form of V, the component form of vector V, is equal to angle bracket v1, v2, close angle bracket. The coordinates v1 and v2 are called components. The coordinates here are called components there. Okay. If both the initial point and terminal point lie at the origin, then the vector V is called the zero vector and is denoted by bold 0. It's the only time you'll use a number to represent a vector. The zero vector and its components are 0, 0. Now, there's two bizarre things, maybe more than two, but at least two bizarre things about the zero vector. Can anyone tell me what they might be?
One is bold.
Okay, yeah, it's bold the way you write it. But two things that basically almost contradict our definition of what a vector is. Say again? It doesn't have a direction. How can a zero vector have a direction if its initial point and terminal point is the same one? No direction, and not only that, the zero magnitude. There is no magnitude either. So it neither has direction nor magnitude, and yet you have to have it as a vector. Okay? The reason for that, as Dawson will find out probably before y'all will, to have a what they call a vector space, you have to have a zero vector. You can't have one without it. Okay? We haven't defined that yet. This definition implies that two vectors U, which we represent as U1, U2, and V, V1, V2, are equal vectors. You could also say equivalent vectors, if and only if the U1 is equal to V1 and U2 is equal to V2. Both of those must be true. Okay? You can't reverse them. They would have same magnitude, but not the same direction. So for those two vectors to be equal, the components must be identically equal. Okay. That's why component form is the way to go. The procedures listed below can be used to convert directed line segment to component form and vice versa. Now this time we have P not being necessarily the origin. At some point P1, P2, coordinates of the point P1, P2, and Q has coordinates Q1, Q2. They are the initial and terminal points of the directed line segment, with this one P not necessarily being the origin. Then the component form of the vector V, represented by the vector PQ, is given this way. Its initial component, its first component, V1, would be Q1 minus P1, terminal second component, Q2 minus P2. Now notice, it is important the order that you do these. It's always final minus initial. You find that in physics, you find it everywhere. Terminal minus initial. Terminal minus initial. Terminal first component minus initial first component. Terminal second component minus initial second component. Coordinate. Moreover, the distance formula, you see that the length or magnitude of V is, magnitude of V would then be this difference squared plus that difference squared, which would be V1 squared plus V2 squared. Now, just a little note here. The magnitude of a vector does not change if you reverse those orders, okay? Or reverse how you add them, okay? Because you're squaring and adding and then taking the square root. But to be consistent and not be sloppy when you get to other things about it, it's usually a good idea to leave them in that way. So it doesn't matter when you're doing magnitude, okay, or distance. Any questions? Because the distance, the magnitude's always positive. Now, that's one procedure. Here's a second procedure. Okay? If vector V, bold V, which is V1, V2, represented by those two components, if that vector V is represented by those two, then V can be represented by the directed line segment in standard position. Now this is going the other way from what we just did. Put initial point P at the origin, then you know what Q is going to be. Its coordinates will be exactly what the components of that vector is, if the initial point is there. Now, let me see if they've been consistent this way. Okay. I can't actually see that they have. In this representation, they made the components of a vector italicized, but the coordinates of a point I don't know, slanted maybe, but not necessarily italicized. I don't put any water in that, because I don't think they're being completely consistent here. So that's not a big deal. The length of vector V is also called the norm of that vector V. Okay? You'll be using that a little bit later on as well. Now, what that isn't is the normal of V. Don't confuse norm with normal. So, if the magnitude of V is 1, okay, new sentence here. The magnitude of V is 1, then what do we call that vector V?
0. A unit vector.
A unit vector. Uno meaning 1, unit, that's a unit vector. Any vector whose magnitude is 1 is a unit vector. Now, don't get that confused with a standard unit vector. We'll talk about those later too. Now,
so it's only 1 is a unit vector. Right?
The magnitude of 1 is a unit vector.
Right. None of the other.
If the magnitude of a vector is 1.01, not a unit vector. 0.999999, not a unit vector. Only if the magnitude is 1. What's that?
Does it matter what the length is?
That is the length. The magnitude of a vector is the length of that vector. And if it's identically 1. Now that 1 could be pointing this way, this way, this way. All those are unit vectors as long as that length is 1. The standard unit vectors or be in the X, Y, and Z direction, or if you're in different coordinate systems, others, okay? but that if the magnitude is 1, it is a unit vector. A unit vector, not the unit vector. Now, if the magnitude of V is 0, guess what? Magnitude is 0 if and only if V is a 0 vector. Bold 0, okay? So magnitude equals 0, that's a scalar quantity. So that's a regular 0. Then the 0 vector is bold 0. That is the only time you'll use a number to represent a vector that I can remember. Okay. Now, they're skipping example 2. I just wanted to make sure I hadn't missed something. Skipping example 2. So let's see if we can go back, find enough white space to do example 2. That may be most of what we can get. Here's example 2. Find the component form and the length of vector V that has initial point let's call it P of 3, 7, 3, -7, and terminal point, let's call that Q of -2, 5. Okay, we first want to find the component form and magnitude. Okay? Let's go for component form first. What would be the component form of this vector V?
So we have to do that formula, the square root.
Okay, the square root thing will give you the magnitude. I'm looking for component form first.
So that's the slope.
What's that?
So that's the slope.
You don't need the slope. It's sort of in there inherently, but you don't actually need it.
The x term and subtract them together, and the y term and subtract them.
Okay? And what do you mean by that? Give me,
So
use.
like a -2 minus 3.
Perfect. And what's -2 minus 3?
-5.
Okay, next.
5 minus 6, 7 is 12.
That's it. There's a component form of that vector. Okay? You see what he did? Always terminal minus initial. First component, -2 minus 3, that's -5. The second component is terminal 5 minus a -7, positive 12. You see that? Now that you have that, it's pretty easy to find the magnitude of V. And what would that be? Square root of -5 squared plus 12 squared, which is the square root of 25 plus 144, which is the square root of, which is 13. Perfect. Its magnitude is 13. Don't know if you've noticed it or not, this is one of those Pythagorean vectors, you might say. 3, 4, 5 is a Pythagorean triangle. 5, 12, 13 is a Pythagorean triplet, they use the color. Okay? That was example 2. Any questions on example 2? So again, once you have it in component form, the magnitude is really easy. If you had done magnitude first, then you would have done this minus that squared, the square root of this minus that squared plus this minus that squared. You done all that work and stuff and got to that. And then you'd have to go back and do this minus that minus that, and do component, which you had already done, but this way you don't do anything twice. You just go for it. Okay. So that was example 2. Now let's move back to where we were. Vector operations. Here's the definitions of vector addition and subtraction. No, I'm sorry, vector addition and scalar multiplication. These are the two primary operations you have with vectors. Later, Dawson will be able to tell you all about vector spaces. These are required for any vector space. We're not there yet, but we will be. So let's start with U being standard component form, U1, U2, V being V1, V2. Those are both vectors. C is a scalar. Okay? The vector sum of U and V is simply, of course, U plus V, is add the first components together, U1 plus V1, comma, add the second components together, U2 plus V2. That is the easiest way to add vectors. Add their respective components. It's that simple. Okay? Now the scalar multiple of a vector and of a scalar multiple of some scalar, C, with either vector, they're choosing U, that is CU, that's a scalar multiple, C times U, would be C times U1, comma, C times U2. It's kind of like you distribute the C across the components of the vector. Okay? Now, here's a couple of more important vector operations. The negative of a vector, either U or V, it doesn't matter, they just choose to do V on this one. Negative V would be, just treat this negative as a scalar negative 1, and then distribute it. And that would be negative V1, negative V2. Okay, now what does that do for you? If V1 is doing like this, V2 will be going just like that. Same line segment with the arrow on the opposite ends. That's the only thing that's changing to negate the vector. Magnitude will be the same, and the direction will be exactly opposite. So that magnitude and this magnitude are the same, but those aren't opposite directions. This magnitude and that magnitude, those vectors are negation. Now, let's go to difference of two vectors, U and V. How do we define the difference of sign numbers? The difference of sign numbers. You take the first number, which in vectors will always be the terminal part, okay? Whichever one, okay. Let's get away from that for a moment. The difference of vectors U and V would be U minus V, okay? That's the difference. Well, how do you do the difference of sign numbers? It's take the first number and then add the opposite of the second number, the negative of the second number. So the difference is adding the negative, right? Same thing here. The difference of two vectors is take the first vector and then add the opposite of the second vector. U minus V is the same as U plus a negative V, right? Plus and minus is minus, that will give you this. So what you do is U, and this is even simpler, again, components are the way to go, U1 minus V1, comma, U2 minus V2, okay? You just component by component, U1 minus V1 in angle bracket, comma, U2 minus V2 in angle bracket. Again, component notation is the way to go. Easiest way to add, subtract, multiply, whatever you're doing with vectors is component-wise. All right. Now they get into geometrically. And frankly, I really don't see why they mess with it, but they do. And maybe it's helpful in some circumstances. Okay? The scalar multiple of a vector v is just scaling it up if the scalar is greater than 1, scaling it down if it's between 0 and 1, and changing the direction and doing the same thing if it's a negative, if the scalar is negative. Okay? So the scalar multiple of a vector v and a scalar c is the vector that is the magnitude of c, whatever that magnitude is, times as long as v. So if c is a small number, less than 1, it'll be scaled down. If it's greater than 1, it'll be scaled up. Okay? So if here's your vector v, this is 1/2 of v, exactly 1/2 the magnitude of v. This would be 2v, exactly twice the magnitude of v. This would be a minus v, exactly the same magnitude, but going in the opposite direction. And this would be the scalar, -3/2 times v, would be changing the direction, that's what the scalar does, and then elongating it by 1.5 times. So that would be the geometric representation of scalar multiplication of a small number, large number, negative number. Okay. If c is positive, then CV has the same direction as v, but if c is negative, then it has exactly the opposite direction. Things I've already said about 2 or 3 times. Now, unfortunately, they're going to do this to you too. But it's not a bad thing. It can be helpful in physics and other things. The sum of 2 vectors, the easy way to do it, add the components. Okay? Another way of doing it is represent them geometrically. Okay? Now, here's what you do. If you've got vector u and you're going to add vector v to it, notice they are in the same plane, but that's the only thing they have in common. So if you take vector u and add vector v to it, we take vector v and move it so its initial point is at the terminal point of u, and its terminal point is in the same direction from its initial point as it was. So you haven't changed that vector. Then you connect the line from the initial point of view to the terminal of v. Okay? And that's what they did here. They took vector u just where it was, translated vector v up here, and then the sum vector would be from the initial point of view to the terminal point of v after you made it tip to tail. Okay? Now, could have done the same thing by starting with v and then take vector u and put its tail at the tip of v, keeping the same magnitude and direction, and then done the initial point of v to the terminal point of u. And you see this sum vector is the same as this one. I would call this one v plus u, because they did that. But it doesn't matter, as we'll see later, they're commutative. The addition of vectors is a commutative process. It doesn't matter whether you do u plus v or v plus u, you get the same result. Just because this is located here and that's located there, they have same magnitude, same direction, those are the same vectors. Does that make sense? Now, in physics, sometimes this is helpful to do it geometrically. Most of the time in math, it's so much easier just to deal with components. By the way, this sum vector, whether you did u plus v or v plus u, this is called the resultant vector. It's a diagonal of a parallelogram. If you put U here, V here. Now, what you've done is brought both of them and put them as origin or any common point for initial point. Then you form a parallelogram. U being one side with a parallel U over here, V being this side with a parallel V up here. And that makes a parallelogram. Then the diagonal from the initial points of both of those to the terminal point to the opposite corner, the diagonal corner, that forms your parallel. So sometimes they call this the parallelogram method for adding vectors. Okay. Now, so this shows the equivalence of the geometric and algebraic definition of vector addition and scalar multiplication. They didn't really do much with scalar multiplication except this. Well, right here. If this is U and then K is a number greater than 1, and you multiply that K by the vector U, then I don't know, that looks like it's about 1.3 times or something like that. Whatever it is. This is component vector KU1, component KU2, KU2 here to here. Okay. Not from down here, but from up here. Now, I almost wish they hadn't have done this. What is your geometric representation of U minus V? The way to do this, there's U, there's V. If you put them with a common, both in standard position, okay? Then to add to, or U minus V would take the vector U and subtract from it the vector V. In other words, take vector V, negate it, flip it, so it's same magnitude but in exactly the opposite direction. Then this will be U minus V, and this would be the component U minus V. Now, unfortunately, they did this making it look like a rectangle. It's also going to be a parallelogram, but rectangles are parallelograms. But they made this one look like it forms a rectangle. Not necessarily the case. Okay? This is the component form. Let's see. The subtraction. U minus V, U plus or minus negative V. Same vector. Okay. Now, any questions?
That doesn't look the same.
Yeah.
That doesn't look the same.
Second?
It just doesn't look the same.
I can't hear you.
It doesn't look the same.
What?
Yeah, it doesn't.
This?
Yeah, U minus V and U plus negative V, it doesn't look the same.
Well, here's U, there's V, so negative V would be that direction. So you put the tip of negative V on the tail of negative V on the tip of U, come down here, and then from the tail of U to the tip of negative V, that would be the component. I don't find this useful. I mean, I do by negating and stuff like this. So much easier to subtract the components and try to draw it geometrically. Now, while we're on this page, before we leave it, here is William Rowan Hamilton. Some of the earliest work with vectors was done by the Irish mathematician William Rowan Hamilton. He spent many years developing a system of vector-like quantities called quaternions. And it was not until the latter half of the 19th century that the Scottish physicist James Maxwell restructured his quaternions in a form useful for representing physical quantities such as force, velocity, and acceleration. In other words, he did a mathematical study, not practical, but just pure mathematics, and came up with these rules, which are basically describing vectors that James And by the way, James Maxwell, his middle name is C-L-E-R-K, but you know the Scotsmen pronounce everything. It's pronounced, even though it looks like clerk, it's pronounced Clark in Scottish. Okay, so, but there are two potential paper topics if you're interested, or quaternions if you wanted to write on that. But anyway, wanted to mention those before we moved on. So let's do example 3, which I think is the next thing. Here is a vector v, negative 2, 5, and a vector w, 3, 4. Find each of these vectors. What is a? 1/2 of v.
So you just take half each of those. So
And what would you get?
-1,
-1 is the first component,
2.5.
or 5/2 is the second. Yeah, either one. Either way you wanted to write it, perfectly done. Perfect. Now, what would w minus v be?
You just subtract the x terms and subtract the y terms.
Okay, and what do you get?
1.
No.
Oh wait, w's first.
There's a minus sign there.
5.
5 is the first component.
And -1.
-1 is the second component. Now, don't you wish you had done this using a parallelogram method of some nature? Please say no, okay? So much easier doing component operations. How about this one?
So,
Yes.
you did it like,
Okay, he did it this way, I think. Can't speak for him. You took the W component, first component 3, and subtract from that the first component of V, which is -2. 3 minus a minus 2, 3 plus 2 is 5.
I was gonna ask if W gonna be always, is W always gonna be turned?
Yeah, always whatever's listed first, you do first. That's your. Now, if it's plus sign, it doesn't matter. Minus sign, it matters big time. Okay? Someone ready to attempt C? It's yes in Spanish.
So it would be -2 plus 6,
Yes, and -2 plus 6 is
4,
4,
then
comma,
5 plus 8, which is 13.
5 plus 8 is 13. Perfect. See how easy it is to do with component notation. Did you want to do diagrams of that geometrically? You have to draw V and then draw 2W, double W, and then put them tip to tail and tail. Please say no. Okay. No one wants to do that. Huh?
You should do one like that.
You please do. Okay. All right. Now, let's see if they got them right in the book. They got -1, 5/2, perfect for them, or 2.5 if you want to do it that way. 5, -1 for the B, and 4, 13 for C. They got it right. Good for them. All right. Let's see how they did it here. And I hope they did it by components, but let's see. Yeah, 1/2 of V would be 1/2 of the first component, -2, comma, 1/2 of the second component, 5. And that would be -1, comma, 5/2. Perfect. Okay? P, you start with W, W1, W2, minus V, which is V1, V2, so it'd be W1 minus W2, in other words, 3 minus a minus 2, 5, and 4 minus 5 is -1. Perfect. Any questions? Exactly like was done. And this time they are going to stop and smell roses a little bit. They're going to start and do 2W first, which is twice W. W was 3, 4, I hope. Yep. Double that, you get 6, 8, and then add to that V, which is -2, 5, and that would give you a 4, 13. -2 plus 6, 5 plus 8, 4, 13. Got it. Any questions? All right. Here are some properties of vector operations. We've already mentioned a few of these, but others you'll see. In this case, U, V, and W, all bold lowercase letters, those represent vectors in the plane, meaning two component vectors. C and D are two scalar numbers, just numbers. Okay. First operation, U plus V, like we showed earlier, is identically the same as V plus U. That's the commutative property of vector addition. I like to put those last two words on. Okay. Secondly, if you have U plus V, and to that sum you're adding W, you get the same result as if you started with U and added to that the sum of V plus W. Because guess what? You're just adding the component by component. So addition, those components are scalar numbers. You can add addition of scalar numbers is associative, so is the addition of vectors. So this is the associative property of vector addition. I like to put that last in. That's what you're doing, adding vectors. Now, how about this one? U plus a zero vector will give you what? Vector U. Why? Because you're adding to U1, 0, and adding to U2, 0. That would be U1, U2. That's U. Okay? That's U. No, okay. And that's called the identity element for vector addition. Additive identity. I would call it element, that the zero vector is that. Additive identity property. Now, doing just a little bit of monkey business with that, if you add to U the exact opposite of U, what do you wind up with?
Still zero.
You wind up with a zero vector, and why is that? Because if this was U, and add to it exactly that, you go from here to here, and then here to here, you wind up right there with no component in any direction, therefore it's a zero vector. Okay? This is called the additive inverse property. I like that terminology fine. Additive inverse property. Now, here they really are grasping at straws, okay? To have something they can call they don't even call it anything, do they? Okay. If you have scalar C multiplied by scalar D times U, that's the same as multiplying two scalars together and then multiplying that by the vector U. That's the closest you can come to a associative property of scalar and vector multiplication. That's a long way to say it, and maybe that's probably left it blank. Okay? They didn't even name it that way. And again, that's sort of a stretch. Okay? Now, here's a distributive property that if you add the two scalars together, C plus D, and multiply that by vector U, that's the same as multiplying C times U and adding to that D times U. Okay? That is a distributive property, I would say, of scalar addition over scalar multiplication. Adding these and then adding that. Okay? Here's another distributive property. This is C times the sum of two vectors U plus V is the same as CU plus CV. Now this would be this distributive property of scalar multiplication over vector addition. This would be scalar addition over scalar multiplication. Okay, so that is, they just call it a distributive property, but I would say distributive property of scalar multiplication over vector addition. And then number 8, 1 times the vector U is just going to be U, because this is the multiplicative identity element. This should be number 9 in my mind. If you multiply the scalar 0 times the vector U, it's 0 times u1 comma 0 times u2, that's 0, 0, that's the 0 vector. So this would be zero multiplication property. Okay. Multiplying anything by the number, scalar 0, is going to produce the 0 of whatever you multiply. So if this was a vector, that would be the 0 vector. So I really wish they'd have separated these two. They aren't really all that related at all. Now, let's go back before we go to the next slide. Here is a woman mentioned here, Miss Emmy Noether. Okay? Now, she lived at a very prolific time, especially in the world of physics. Okay? She's a mathematician. One person who contributed to our knowledge of axiomatic system was the German mathematician Emmy Noether. She's generally recognized as the leading woman mathematician in recent history. What was that? Oh, I thought you were pointing. Okay. Now, here's how good she was. When Einstein had trouble with math, he turned to Emmy Noether. She was pretty sharp. Okay? They had something else in common. Anyone want to make a guess? If you notice there, German mathematician, he was a German physicist, right? So they're both German. Look at and since they lived basically similar time period, because he turned to her, notice what was going on in that time period, 1882 to 1935. Now, 1935 is a little early on her part. Say again?
The World Wars.
Yeah, okay, certainly both world wars happened then, but specifically the second. Now, okay, we weren't involved in 1935, but it had already begun. What were some of the things happening then? Ah, very good. Both Einstein and Noether were at least part Jewish. Okay? And no matter how bright you were, how accomplished you were, how whatever you were, if you had what the Nazis considered any fairly small fraction of Jewish blood in you, you couldn't be a professor, you couldn't be a performer, you couldn't be anything. You were stripped of all honor, recognition, and everything. And therefore, both of them, bright, incredibly bright people, fled to the U.S. And we benefited big time from Nazi Germany's idiocy. I mean, it's pretty incredible that went on. Now, sort of a difference here between Einstein and Noether. Einstein was very well recognized for his accomplishments. Now, I can't recall if he ever got a doctorate. I know he must have gotten several honorary doctorates. Whether he actually completed a doctorate, I don't know. Noether, on the other hand, because of the time at which she was living, she couldn't even officially attend college. But she was incredibly bright, and some really open-minded, far... Say again? Mostly because she was a woman. This is before the Nazi time. Certainly when Nazis came into power, the Jewish thing was there too, but that would have applied to Einstein as well. But because she was a woman. But because there were some far-thinking professors at some universities, they let her sit in on lectures, and they valued her input, and that's how she became so well known. Now, when she came over to the U.S., which had a bit more liberal approach to things, she actually went on faculty at a fairly prestigious women's college. I'm not sure if she would have been able to do it at a man's college, but she did go at one. I can't think of the name of that school. It has an unusual name. Bryn Mawr or something like that. Bryn Mawr. Very Irish or Scottish sounding name, I don't know. But anyway, both of these, if you'll notice here, under both Hamilton, it says see larsingcalculus.com to read more of that biography, and underneath hers you'll see for more information on Emmy Noether, here's the article, Emmy Noether, Greatest Woman Mathematician, by Clark Kimberlin, blah, blah, blah. Now, the book cannot be your source for a paper topic. This can give you some great ideas for your, cannot be the source for your paper, but can give you great ideas for the paper topic. So both of those are quite nice. Now, and then there's one other thing said here, and here it is. This is very bottom of page 755. Any set of vectors with an accompanying set of scalars that satisfy the 8 properties listed here, these 8 properties, okay? And notice, basically, 4 of these are strictly addition, subtraction type things, mostly addition. These involve some type of multiplication, all of those, okay? But any set of vectors with the accompanying set of scalars that satisfies those 8 properties listed in 11.1 is called a vector space. Now, included in that was your linearity, which is the addition properties and your scalar multiplication properties. That makes a vector space. And you'll be dealing with that in a late chapter. Okay. The 8 properties are the vector space axioms. This is where Emmy Noether came along. She was really big on developing axiomatic proofs of things. So this theorem states that the set of vector in the plane with the set of real numbers forms the vector space. So here's another theorem. The length of a scalar multiple. Okay? Now here's a vector V. V be a vector. C be a scalar. Then the magnitude of C times V, the scalar multiple of scalar V times vector V. Another way to do this is just pull out the V, but pull out the absolute value of V times the magnitude of V. Absolute value of C times the magnitude of V. Okay. Why? Because any magnitude has to be a positive value. And if C was a negative quantity, in here it's changed to positive, but here you would have to have the absolute value of C times the magnitude. Okay. Now, that was top of page 756. Here's a little bit further down. In many applications of vectors, it is useful to find a unit vector that has the same direction of that given vector. Any old vector is not necessarily a unit vector. So to make it into a corresponding unit vector, here's what you do. The next theorem gives you this procedure. If V is a non-zero vector, okay, you can't make the zero vector into a unit vector. No way. Okay, no way. So V has to be a non-zero vector in the plane. Then the vector, I don't even think you need to say that, but then the vector U, now before U was any old vector, now this U is a unit vector. How you get it? Take the vector V divided by its magnitude. Okay? Now, another way to express this is 1 over the magnitude of V times the vector V. Now, if you think about this, this vector here has to have a length 1. because this is 1 over this, so this is going to be the magnitude of the vector. And if you did the magnitude of this thing, that can come on the outside, because that's just a scalar quantity, and this would be the magnitude of the vector. Well, the magnitude of v over the magnitude of v is 1. So the magnitude of u would be 1. And it has the same direction as v, because you're multiplying v by just a scalar, a positive scalar quantity. So here u is called the unit vector in the direction of v. That process of multiplying v by 1 over its magnitude, vector v by 1 over its magnitude to get a unit vector, is called the normalization of v. Now, I'm going to fly back for a little bit, so hang with me, and let's see if we can find it. There it is. The length of the vector is called the norm of v. That's the length of a vector v. Okay? Don't get that confused with the normalization of v.
Which would be v divided by 1.
By its own magnitude. Okay? Okay. So the normalization in this sense means made to be 1. That's what normalization means here. Norm back there just meant magnitude. This is made to be magnitude of 1. Get it? The process of multiplying a vector by 1 over its magnitude normalizes that vector or makes it magnitude 1. Makes it into a unit vector. Okay. Generally, the length of the sum of two vectors is not equal to the sum of their lengths. Yes?
Skip example 4.
Oh, sorry. It's so easy because, yeah. Is it example 4? Yeah, you're right. Yeah, that goes right here. So let me back up and do example 4. Whoops, this looks like the most white space that's readily available. All right. Find the unit vector in the direction of v. Here's vector v is equal to negative 2, 5. I think they like that vector, don't they? I think they've used it several times now. Now, and then we're going to verify it has a length of 1. If it doesn't, it's not a unit vector. So what would be the vector u? Well, you don't have to name it that. Let's just find the unit vector in the direction of v. What would it be? What's its definition? V over magnitude of v, right? Okay. Okay. So this would be the vector v divided by the magnitude of the vector v. So what's one thing you got to do? Find this magnitude. So what is that? Magnitude of v is equal to what? Square root of magnitude of v.
Negative 2 squared.
Second?
Negative 2 squared.
Okay, negative 2 squared plus 5 squared, which would be square root of?
29.
Second?
29.
29. Got it. So here's what we've got. We've got the vector v, which is negative 2, 5, divided by root 29. Now, I was from Georgia, and in my first class today, a guy came in with his University of Georgia stuff on because he knew I was from Georgia Tech. And I remember a friend of mine whose uncle graduated from Georgia Tech used to say, only good thing to come out of Athens, which is where Georgia is Route 29. Okay, so this is Route 29. The only good thing to come out of Athens, Georgia. Never. Dumb joke. Okay, now, what you can do here, this is the same as 1 over root 29 times the vector negative 2, 5. Perhaps I should have written it that way. Well, then you can distribute that scalar, that's a scalar quantity, inside, and this would become vector minus 2 over root 29, comma, 5 over root 29. Okay. Now, any of those representations are fine. This may be the best one to do what the second part was. It says, verify it has a length of 1. So what would be the length of this vector? What's that? Okay, I can't hear you. What you say? Okay. So what will you do to get its magnitude? Square root of negative 2 over root 29 squared plus 5 over root 29 squared. And what would that be? Square the numerator and you get 4. And square the denominator, you get 29 plus 25 over 29, and that would be 29 over 29, which is 1. Square root of 1 is 1. What's that?
Your 25 looks like it's 24.
I can't hear. That? Is that what you're talking about? Sometimes the pen drags. Okay. We verified that is indeed a unit vector, and it's in the same direction of the initial vector. It's just 1 over root 29, the size. Okay. Now we can go back. Now, y'all have to keep up with time for me. How are we doing? 14 minutes to go? Okay, thank you. Someone's really watching, huh? Okay. All right. This is what before I got it, realized, Fred told me we were off track, skipped a example. Here's a slide. Generally, the length of the sum of two vectors is not equal to the sum of their lengths. Because most of the time, your two vectors don't necessarily have to be collinear. Most of the time, they won't be. They'll be any directions and stuff. So what, then, if you added the sum of their lengths, that would only be true if they were in the same direction. Sum of this length plus the sum of that length would be the length of the sum. If they're any angle other than 180 degrees, then they won't be. To see this, consider these two vectors, u and v. Here's u, there's u, and here's v. Now, the sum of these two vectors is u plus v, just like we've done before. Well, the magnitude of this plus the magnitude of this would be something like that, which is considerably longer than this. Okay, I don't have long enough fingers to do that exactly, but we can look at that. Now, that is called the triangle inequality. Let me get it up here for you. When u and v are two sides of a triangle, the length of the third side, u plus v. Now, notice, to be a triangle, there has to be an angle in there. It can't be a straight line. So, if this will negate the chance of even equality. The magnitude of u plus v is always less than or equal to okay. The magnitude of u plus magnitude of v. Equality occurs only. The equality is there only when the two vectors u and v have exactly the same direction. Then these two magnitudes have to be the sum. The result of this is called the triangle inequality for vectors. Notice for the equality to be true, it won't be a triangle. It'll be a straight line. Okay. Okay. Any questions on that? Now, we move to the topic I alluded to earlier, standard unit vectors. Here in the plane are these two unit vectors, 1, 0, and 0, 1. Those are called the standard unit vectors in the plane, and they're denoted by little I, bold little I, okay, and bold little j, because they are vectors. Now let me say something I do. This book doesn't do it. I've seen other books that did, but I like the idea of it. Let's go back, if we can, to this one, okay? If I know that this u is a unit vector, here's how I'm going to write it. I won't write it as vector u, I will put caret on top, you know, mountaintop, that kind of thing. To me, that indicates it's a unit vector. That reminds me it's a unit vector, okay? Any old vector u would have just an arrow on top. Vector v would have an arrow on top. But if I know it's a unit vector, I put a caret on top. Okay. So when I write I, because remember I can't write bold, I don't write just I with an arrow on top. I write I with a caret on top. And I write j with a caret on top. To remind me, even though you don't need reminding, I don't think, for I and j, these are unit vectors. These are your standard unit vectors because, of course, what's the magnitude of this one? 1. And the magnitude of that one. 1. But they each have a component of 1 only in one dimension, and the other dimension is 0. Those are your standard unit vectors. Here's I in the x direction, j in the y direction. Standard unit vectors in the plane, I and j. Now, you don't have to write carets. I don't demand that, but I do. So when you see it on your test, I like to put the caret on top, if I can. Now, some word processing packages don't allow that. So I just do it bold then, because I can't do the other. Okay. All right. Now, what's something special about those two unit vectors? If you've done any physics yet, you probably already run into this. These vectors can be used to represent any vector uniquely this way. If this vector v is v1, v2, like we've been doing, angle brackets here indicating it's a vector, that would be the vector v1, 0 plus vector 0, v2. Because to add these two together, you'd add the first components, that gives you v1, second components, that gives you v2. So that gets you right back where you started. But now that the only scalar value you have in there is v1, pull it on the outside, and that's v1 times 1, 0 plus v2, the magnitude of your second component, times 0, 1. And you pull that out. So what do you have? v1i plus v2j. So that, okay. Back when I was a boy child in college and first dealing with vectors, this is what we called component notation. We didn't have the angle bracket notation. I don't know if the books I used just didn't have them or they hadn't come up with it yet. So this is what I would have considered component notation, because it's just component v1, v2. Because we didn't have the angle bracket that I remember ever seeing before I started teaching out of more modern text. Okay, so this vector v, v1i plus v2j is called the linear combination of your unit vectors I and j. Okay, the scalars v1 and v2 are called the horizontal, because that's the I component, and the vertical components of the vector B. And you do use these in physics big time. Any of you had your physics yet? Or having it now?
Yeah, we're in physics.
Huh?
Which physics? We're in physics now.
Physics 1 or 2? 2. Okay, then you've already run into it in physics 1 big time. You had physical science and didn't really get into that too much. Okay. Example 5 is next. How are we doing on time? 6 minutes. Okay, let's see if we can get this one done. Let U be the vector with initial point 2, -5, terminal point -1, 3. Let's let vector V be 2I minus j. Write each vector as a linear combination of I and j. So what would U be as a linear combination of I and j? So what would vector U be? Now that's not a unit vector. See, a lot of times the book will use U for a unit vector, other times it won't. So that's why I like to use arrow or caret so I can know which one I'm talking about. This is any old vector U. What would it be based on what they told us here? Initial point 2, -5, terminal point -1, 3.
B2 minus 1.
Say that again.
B2 minus 1 and -5 minus 3.
Okay.
Like the little arrow.
Right, except what do we always do? Terminal minus initial. Remember?
Okay. -1 minus 2.
Okay, so that would be
-3.
-3, comma. Second,
Positive
8. Perfect. Okay. Now, let's write that in as a linear combination of I and j. And that's easy. What would that be? -3i plus 8j. Perfect. You could have done that all at once, but I think it was a little easier doing it that way. Okay. Now, how do you figure out what W is?
You can plug in what we just got.
Yes. So let's do 2 times. Now, do you want to use the component notation or the linear combination? Really doesn't matter which way you want. Yeah, let's go on and use it since that's what you're gunning for at the end. Be -3i plus 8j minus 3 times 2i minus j. Okay, how do you eat your 5,000-pound elephant? One bite at a time, so let's just take it one bite at a time here. What do you have here? -6i plus 16j, -6i plus 3j, and then that would give you -12i plus 19j. All right. How did they do? It looks like they got it right in the book, didn't it? Good for them. So proud of them. Everybody see how that works?
How often do we have to do that when V will be equal to I minus J?
Say that one more time.
How often will we have to do that when V is equal to 2I minus J?
I don't know. I mean, many times as you want to. I don't know. That is the old standard way of writing what I used to call component notation. Okay? That shows you the components of the vector by their unit vectors, which is exactly the same as 2 minus 1. Okay? So, in physics, haven't you done that? Don't you have the IJ notation?
I don't know what Mr. Brown is talking about, but I'm glad you
Okay. All right. Let me erase this because we are, I'm sure, running pretty close to out of town now, right? Let's see how they did it. Say again?
Are we at a 210 or 215?
210.
Oh, yeah, we're out of time.
Is what?
We're out of time right now.
Okay, well, no extra charge for this, okay. This will be Q1 minus, in other words, remember it's final or terminal minus initial, so it would be Q1 minus P1, comma, Q2 minus P2, which in this case was minus 1 minus 2, comma, 3 minus a minus 5, so that would be minus 3, 8, which would then be minus 3i plus 8j. I think that's exactly what we got, right? And then W to U minus 3V, that would be 2 times U, which we just did, just like Patrick was doing, negative 3i plus 8j, minus 3 times 2i plus minus 2j, minus j, which was given, minus 6i plus 16j, minus 6i plus 3j, which gave you minus 12i plus 19j. Good. Okay. Unfortunately, the next slide starts at the top of page 758, but we've still got to do the bottom example of 757. So we'll start right there next time. But let me give you a few homework exercises to work on. I know you'll be disappointed not to have some. You can do 3. It's at calcchat.com. 5 or 7, they're both at calcchat. 5's at calcview. Any of the odds 9 through 15, they're all at calcchat. 11's at calcview. 17's at calcchat. 19 through 23 are at calcchat. 21's at calcview. 25's at calcchat. 27's at both calcchat and calcview. 29 to 33 are both all at calcchat. 35 or 37 are both at calcchat. 35's at calcview. 39 or 41 are at calcchat. 43's at calcchat. 45 and 47 are at calcchat. 47's at calcview. 49 and 51 are at calcchat, with 49 being at calcview. 53 and 55 are both at calcchat. Wait. I think we may have gotten into... No? It's a notation we haven't seen before, but it is something we've done. 53 and 55 both at calcchat. 57 and 59, you can explore doing those if you choose. 61 through 65 are all at calcchat. 67 and 71 through 71 are all at calcchat. 73 is at calcchat. And 75 is at calcchat. Actually, 75, 77, 81. Yeah, it seems like they've skipped some things here. Let's just stop somewhere back there. Maybe find the unit vector, 71. Let that be the last one you do, and we'll pick up the rest of those. Okay? Good deal. All right. We got to quit having one day class a week. Next week we'll have it twice. Okay. Good deal. And we'll see you tomorrow.